Hello everyone, welcome back to DKodeTree. Today I will be solving Leetcode 142 linked list cycle 2. This is a sequel to the problem Leetcode 141 linked list cycle, which we have already solved in the previous video using the fast and slow pointers technique. This problem is another very interesting application of the fast and slow pointers, and we will not only solve it but also understand the intuition and the proof behind the solution. In this problem, given the head of a linked list, we need to return the node where the cycle begins. Which means if there is a cycle in that linked list, then we have to return the start node of that cycle. And if there is no cycle, then we will simply return null. The easiest way to solve this problem is to traverse through each node in the linked list one by one while keeping track of the already seen nodes in a hash set. Initially we have an empty hash set and we start traversing our linked list from the first node 3, and we can see that our hash set is empty, so obviously we have not seen 3. So we'll go ahead and add the node 3 to our hash set. Then we move to the next element 2, and we can see that 2 is not present in our hash set. So we'll go ahead and add the node 2 to our hash set. Next we move to the node 0. Also we can see that node 0 is not present in our hash set. Add it to our hash set again. Next we move to the node -4, and -4 is also not present in our hash set. So we'll add -4 as well here. Next we again move to this node 2. Now we can see that node 2 is already present in our hash set, and this lookup we can do in O of one time. As this node is already present in our hash set, so obviously there is a cycle. And since it is the first time we are seeing a repeated node, so it must be the start of the cycle. So whenever we see the first repeated node, we return it as our result. This approach is very simple to implement and it works in O of n time, as we are scanning through each element in our linked list at least once. But this approach requires O of n extra space as well due to the use of this visited hash set. And it turns out that we can further optimize the space complexity to O of 1 by using the classic two pointers technique called the slow and fast pointers algorithm, also known as the Floyd's Tortoise and Hare algorithm, just like we did in the previous problem. I will explain how the fast and slow pointers help in solving this problem as well as the proof behind why it works. The idea is to solve the problem in 2 steps. In step 1, we will detect whether there is a cycle or not. And if there is a cycle, then we will move to step 2 and find the start node of the cycle. And if there is no cycle, we will simply return null. This first step is exactly the same as we did in the previous problem. We take 2 pointers, slow and fast. Initially, both of them will be at the head. Slow moves by 1 step at a time and fast moves by 2 steps at a time. So we can compare the slow with the tortoise and fast with the hare. And while traversing the linked list, if at any point both the slow and fast pointers meet, then there is a cycle. So initially both the slow and fast pointer are pointing at the head. At each iteration, we move slow by 1 step and fast by 2 steps. So slow is at 2 and fast is at 0. And we repeat the process. We move slow by 1 and then fast by 2. So fast moves to -4 and then 2. We again repeat the process. Slow moves by 1 step to -4 and fast moves by 2 steps to -4 as well. So we can see that this is the point where slow and fast are meeting. So even though slow and fast are moving at a different speed, but they are meeting inside the linked list, therefore there is a cycle. Till this point, I have explained the entire process in detail and the intuition behind why this works in different cases with examples in the previous video. So you can find the link of that video in the description. So now let's move to the next step. So once we know that there is a cycle, we need to find the start node of the cycle. To do this, we take another pointer, say slow 1, and we place it at the head of the linked list. And we keep our fast pointer untouched. Now we move both the pointers slow and slow 1 by 1 step at a time. And the node where the slow and slow 1 meets is the start of the cycle. So let's continue this example and verify it. So we move slow 1 by 1. So slow 1 comes to 2 and also the slow pointer by 1. And we can see that the slow pointer also reaches 2. In this case, this is the point where these 2 pointers meet. So this is the start of our cycle and we will return node 2 as the result. If we look at this example, we can see that this is actually the start of the cycle because this is the point from where we are entering into the cycle. Now let's understand why this algorithm works. This algorithm works because both the slow pointer and slow 1 pointer takes the same amount of step to reach the start node of the cycle, although they are starting from two different points, as the slow one is starting from the head and the slow pointer is starting from the intersection point of fast and slow. So the number of steps the slow pointer takes to reach this position turns out to be the same as the number of steps the slow one pointer takes to reach this position. So now let's understand this mathematically, that why this is the case. Suppose in the first step, this is the point where both the slow and fast pointer met. And this is the head of the linked list. And this is the start of the linked list cycle, which we will finally return. Let's say x is the distance between the head of the linked list to the start of the cycle. And let the length of the cycle be c. And let's denote this distance from the intersection point of the slow and fast pointer to the start of the cycle be y. So our intention is to check what is the relation between the x and y. And for our calculation purpose, let's denote the remaining distance, that is from the start of the cycle to the intersection point, as z. Now note that if this entire circle is of length c and this part is y, then z actually becomes equal to c minus y. This equation will come in handy while understanding the proof. Also, we know that in the first step, the distance traveled by the fast pointer is actually twice the distance traveled by the slow pointer, because the fast pointer is actually traveling at twice the speed of the slow pointer. Both the pointers are starting from the head, but the slow is moving by one step and fast is moving by two steps. So let's fill up this equation and see what we get using the distances that we have plotted here. So in this case, the distance traveled by the fast pointer from the head is actually the distance x plus some constant amount of times around the cycle, which we can denote as k1 into c. So k1 is a constant and c is the cycle length, plus this additional distance z, because this is the point where the fast stops. Similarly, the distance traveled by the slow pointer is x plus some other constant, say k2 amount of times around the cycle, plus z to reach the intersection point. So now let's put these values in our equation. So this becomes x plus k1 into c plus z is actually 2 into x plus k2c plus z. Now we just need to solve this equation. So x plus k1c plus z is equal to 2x plus 2 into k2c plus 2 into z. Now let's move all the x's on one side and the remaining terms on the other side. k1c minus 2 into k2c plus z minus 2z is equal to 2x minus x. Now on taking the c common, it becomes k1 minus 2 into k2 into c minus z is equal to x. So in this equation, now let's see what is the value of z. Earlier we already found that z is equal to c minus y, that is the length of the cycle minus y. So we'll just replace z equal to c minus y in our equation. So on replacing z with c minus y, our equation becomes k1 minus 2k2 into c minus c minus y equal to x. So let's just simplify this. k1 minus 2k2 into c minus c plus y is equal to x. So if we take the c common from these two terms, it will become c into k1 minus 2k2 minus 1 plus y is equal to x. Now here remember that both k1 and k2 were two integer constants. So this entire term k1 minus 2k2 minus 1 will also be another constant integer. Say it's k3. So the equation now becomes c into a constant k3 plus y is equal to x. So this is our final relation between x and y. So now let's see what this means. So here you can see that c means the length of the cycle and k3 is a constant integer. So this term c into k3 actually means some certain count of rounds around this cycle. So if k3 is equal to 0, we get y is equal to x. If k3 is equal to 1, we get c plus y is equal to x. Similarly, if k3 is equal to 2, the equation becomes 2 into c plus y equal to x. So for all these three examples, we can see that either x is equal to y or x is equal to sometimes around the cycle plus y. To make it more clear, I have also added these two examples. The first one is an example of the case where k3 is equal to 0, and we can easily verify that both x and y are at one step distance from the start node of the cycle. So that implies x is definitely equal to y. And the second one is an example of the case where k3 is equal to 1. From the diagram, it's clear that length of the cycle c is equal to 3 and the length x is equal to 4. And if you simulate the slow and fast pointer movement on this example, you will find that this is the intersection point, and from here the distance y is equal to 1. And if you fill up these values in this equation, you can easily see that this equation still holds. In this example, the slow pointer takes one round around this cycle, covering a distance of 3, plus it covers the distance y, that is 3 plus 1, 4, which is exactly equal to the value of x. Another point to note is that in this example, the reason of taking a round around this cycle by the slow pointer is because the length of the cycle is actually less than the length of the chain. So it is very obvious that the slow pointer, which will be starting from this intersection point, needs to take at least some rounds around the cycle to reach the start node at the same time when the slow one pointer will reach by traveling the distance x. You can try simulating this with different examples, but this final relation between x and y will hold true each time as we derived it from this base equation. So depending on the value of k3, x and y can be equal or x can be equal to y along with some rounds around the cycle. So whatever the value of k3 is, the slow pointer will definitely travel this y distance and slow one pointer will definitely travel this x distance. By the time the slow one pointer reaches the start node, the slow pointer may or may not take some rounds around the cycle, but it will definitely cover this y distance and reach the node S. So whatever the value of k3 is, the number of steps this slow pointer needs to reach the start node will be exactly same as the number of steps this slow pointer needs to reach the start node. The only difference is depending on the value of this k3 constant, this slow pointer may or may not take some rounds around the cycle along with covering the distance y, which will not make any difference in the calculation. I hope it is clear from this explanation that why these two distances are considered same each time, as this is the essence of why this algorithm works. This slow and fast pointers method runs in linear time because in worst case we traverse the linked list only a constant number of times. And in terms of space complexity, it only takes a constant amount of space because it's not using any extra data structures other than these three pointers. So now let's code up this solution. So the first step in our solution is to detect the cycle. For this, we will be taking two pointers, slow and fast, as we discussed, and point both of them to the head of the linked list. Now we will run a while loop which will execute only when the fast and fast.next are valid. So once we are inside the loop, we will increment our slow pointer by 1. So slow is equal to slow.next, and we will increment our fast pointer by 2. So fast is equal to fast.next. As we are moving our fast pointer by 2 steps, that's why we need to explicitly check whether fast.next is also valid. Now if at any point the slow pointer meets the fast pointer, that is slow is equal to fast, in that case we have detected a cycle. So once we have detected a cycle, we will implement the step 2, which is finding the start node of the cycle. We have two options. One is to implement the second step inside this if condition only. Otherwise, we can break out of the while loop and implement it separately as well. So I will show you both the ways. So suppose we are implementing our second step inside this if condition. So for this purpose, what we will do is we will take another pointer, slow one, and we will point it to the head of the linked list. Now as we discussed, we will move both our slow and slow one pointer by 1 at each step. So we will run another while loop with the condition slow not equal to slow 1. That is until slow and slow 1 pointers meet. And as we know that there is a cycle, they will definitely meet. If they are not equal or if they have not met, then only we will move our slow pointer by 1. That is slow is equal to slow.next. And we will also move our slow 1 pointer by 1. So slow 1 is equal to slow 1 dot next. We will exit this while loop only when this condition is false, that is slow 1 and slow are at the same position. So once we are out of this inner loop, we can simply return either the slow pointer or the slow 1 pointer, because both will be pointing at the same node. So once we have completed this loop, that means both the slow pointers are at the same position, and as per our algorithm, it is the start node of the cycle, and we can return any of them as our result. Now, if we get out of the entire loop without returning anything, that implies either fast or fast.next has become null. And this can only happen when there is no cycle and we have reached the end of the list. So in such case, we will simply return none as the result. So this implies the case where there is no cycle. So let's run our code. We can see that this works fine. Now let's quickly see how to implement the second version, that is implementing the second step separately outside the while loop for step 1. So the code will change from here. So for this, we will remove this part entirely, and once we have detected a cycle in the outer while loop, we will simply break out. So once the cycle is detected, we are out of the while loop. But there are actually two cases when we are getting out of the while loop. One is if there is a cycle getting detected inside this if condition. In that case, we are breaking out. And there is another case where we are naturally exiting the while loop. So if we are naturally exiting the while loop, we can use this condition, that is while else. This while else condition will only run if the while loop ends naturally without a break. In that case, we will simply go ahead and return null. So this is the case where there is no cycle. This statement will only run if the while loop ends naturally without a break. So now let's move to the step 2, that is finding the start node of the cycle. Here we will simply take another pointer as we did in our previous implementation, that is slow 1, and point it to the head of the linked list. Now we'll run a while loop which will run till slow is not equal to slow 1. And inside the while loop, we will move both the slow pointers by 1. So slow will move to slow.next and slow 1 will move to slow 1.next. Finally, once we reach this position or get out of this second while loop, that implies that both slow and slow 1 pointer are at the same position, that is the start node of the cycle. So we can simply return any one of them as the result. Note that the control will reach the step 2 only when we have not returned none in the previous section. So therefore, this will only get executed if there is a cycle present. Now let's run this. We can see that this is also accepted and it's efficient in terms of both space and time complexity. So if you found this helpful, give this a thumbs up and subscribe to the channel for more such videos. I have added the solutions for this problem on my website DKodeTree.com. Feel free to check it out. Thanks for watching. See you in the next one.